You should. Now, you should have an image again. I first try to show you some tests in practice, but I found that it was difficult to show because my letter type is too small. Can I enhance, make it bigger? Yes, would be. Could it be done? What is the best thing to make it bigger? Does it make sense? Not enough to be read, isn't it? I'm afraid? No. Anyway, then I don't do it this way. But I just can read it to you. This file input output is a subtest of so-called SeeStats, a test of Trevor Hemsley, or shoot of tests. And you see that in this case the program is writing to disk. It first does 4 kilobytes sequential write uncatched. It means it just writes to the file system, not to the cache, but to the file system. And it can do that at speed is about 1300 kilobytes a second. Then it tries to read those files from the file system, and the speed is about 1500 kilobytes a second. Then it tries to do the same with random uncatched stuff. Writing is about 600. So it's slow, it's one of the slowest things it does. Writing randomly at a complicated file system is very slow. If you do it uncatched, it just means that it's randomly, so it's scattered around the disk. It's not just one piece let down, just like a car jumping. It's stuff, say sand on a hill, but it must be put down neatly in the file system. It costs time. Random reading it is much faster, and that's, I think, really a feature of the file system, because if you would do this on FAT, it would be terribly slower. Then it's also making use of cached writing, and now we have 50,000 kilobytes a second. Well, that's almost or more than bus speed on this computer. Then it reads it sequential, and that was remarkable. I expected a very high input-output, but it was 8,000. I have no explanation for that. If you go further, it goes to the random cached thing, and that's going very, very fast. If I see it, it's about 160,000 kilobytes a second, so 160 MIP a second. So that's really, really fast. There was just one problem. The problem was that the computer will hang. Why is that? And what is the hanging? Now I really must go to the presentation again. The point is that the cache works in kernel memory. We don't have a pointer here. There was no. We have already seen this. You had seen earlier presentations that the cache runs in memory. It also means all things that happen in kernel memory, or important things that are done by the kernel is uninterrupted multitasking. You don't interrupt the kernel. When it's kernel, just the boss, don't disturb it, the door is closed. If you have a problem, a message for the kernel, you put it in a kind of input-output queue, but you cannot disturb the kernel. It means that if the cache is being read by many files randomly, well, if you have a large cache, it just can accept quite a lot of messages. Maybe it accepts a few thousand of files and says, well, I will do that lazy write. But when it comes to the job, many small files laying down on a large file system, just using DMS speeds, but also using the very complicated file system structure, you cannot do that as fast as you can do things in memory. So what happens then? The cache has to synchronize. And before it first has to synchronize before you can say, oh, we can go on accepting further calls. Now, if it synchronizes, it doesn't want to be disturbed. I just made a picture of it. Here's the situation. In this case, I had a picture taken of it with an SMP kernel. One core is 100% busy and the other core is still working, so that I could use PMView, otherwise I couldn't use PMView. What happens when the kernel really stalls because it's busy with, in this case, this task, 4 kilobyte random cached read, which doesn't have yet an output for that, is that well, it's just 100%, in this case, just one core is 100% busy. And if I only had one core, oh, it was here, I must look now. If I only had one core, I could do Ctrl-del or try the watchcat key, and I only get a beep, but nothing happens. The system is frozen, just like it is in this picture. After a while, and that's funny, the kernel will stop. It just goes down again. And then watchcat pops up and things run again. And you even get a nice message here. That's funny, isn't it? So what happened is that the kernel was sometimes a few minutes busy with synchronizing hundreds of MIPS of very small files on the hard disk, which is really slow under every operating system. Just said, don't disturb me, busy. And then when it was finished, gave back CPU use to the processors, and you could go on further. Well, if you had an incoming call at that moment via the network, maybe it's lost, but no files are lost, no problems were at all mentioned. Now, this was a thing I could, well, you could, Eugene called me, is it a bug? No, it's not a bug, it's a feature. The kernel is just doing what it has to do. The only problem is that the kernel, that the user doesn't know it. Please don't disturb on synchronizing. So, well, I let down some journal file system performance issues. No journal file systems related trap errors should happen. Well, I must say I see them seldom, and if they occur, I wonder if it's journal file system. There have been journal file systems related traps in the past, and most of them have been resolved by IBM. Nevertheless, you can expect problems with maybe new ACPI hardware, and the other big problem could be, or will be, sharing code with Linux. Why? Because the Linux kernel development or the driver development is independent of the OS2 one. We already had an LVM. Well, Linux LVM is just a different thing. We can only share at partition level, not the whole thing. But also we must be, we could have got more and more problems. Until now I didn't find them. But I'm not safe. Just a picture about catching, because I have a lot of information here, and you can better read it if you're interested at home. Oh yes, this is interesting. Oh, what's it? Unified buffer catch. Seen that? Seen that? Oh yeah, this is an interesting one. This is the problem we see when you suddenly have heavy input-output. Normally, the catch is a segmented catch. In fact, you can see the catch has, I would say, 3 layers. You have a file system here. Then you have a layer of free buffers. The free buffers are, you can compare them with the DOS buffers. Everything has to go through the buffers. If you read in a new file, it must be loaded in free buffers. Then, if it's uncatched, it's also redstone buffers. If you can, DOS diskette you read without catch only in DOS buffers, or in this case OS2 buffers. If it goes to the real catch, it first goes to the so-called probationary buffers. Probationary means newbie. If you are probationary, have a probationary period at your job, you're just in the firm, but you're not definitely established. But if a probationary buffer, just read in buffer, gets a catch hit, it is promoted to the protected part of the catch. Now, journal file system catch is designed in such a way that the protected part of the catch can take up to 2/3 of catch size. So if I have SeeStats, I can, that's catch stats, that's the program here. I mean, does anybody use that utility? It's part of the Open JFS project. It's also part of modern ECS systems now. Just to do a SeeStats on the prompt. Do this again. I could show you how it looks like in my case. Where are you? Well, yes, make it smaller. Just type SeeStats and you get information about catch size. In my case, can you read it or must I enlarge it? Okay, right. Okay, the catch size is in buffers. It means if I have 4 kip buffers, which is the default, I have a catch size of 400 MB. It's 100,000 clear is of English. 100,000 buffers of 4 kilobyte. The protected part of it, the part which had 1 catch hit at least, is that one. 15,000 plus about 3,000. So only a very small part of the catch. The sum is found in the so-called SLRU run 16,719. That's just the sum of that one and that one. The protected C buffs and the protected C buffs and the protected G buffs. So-called C buffs it's mostly data. So-called gbufs is mostly metadata. I can show you. Well, first do SeeStats again. See if everything has changed. Now you see, for instance, that gbuf protected have not changed. Yes. Now, if I now open a drive on journal file system, a large drive with backups, it should be that gbuffers must be enlarged. Well, you see here and there, gbuffs protected are enlarged, and the gbuffs probationary have increased. If I really stress the system, by, for instance, doing a tree test. Do you know the tree test? It just gives a directory tree and files. Then you also see that, in fact, if you do it on a large petition, in fact, all the metadata of the petition have to be read. It's a nice test to see if your cache is large enough or not. Where's the prompts? Prompts. You now let's go to you. Tree. Now this is the tree test, and I'm afraid I cannot show you the disk input output because I could not enlarge the fonts, because when I enlarge the fonts it run out of the pixels or out of the screen. But during this test you should see that, for instance, the cache stats change because especially the gbuffers will increase. You see it? It's 1400 now, protected ones, and it's 1700 now, and that goes on. And if I do this in the background, it would grow even faster because less processor use is made here by the panorama screen, which is not very fast compared to Cytex. Now you see it's doubled again from 2, 4, 5, 8, 7, etc. All right. So that's a very handy utility, and now it's an interesting thing. We go back to caches. If I do a tree test on my biggest hard disk, I soon have that the protected buffers catching metadata, which are the gbuffers protected, almost fill the cache. It does mean that the amount of metadata to be cached on very large disks is tremendous. That's not a new thing. We already had, for instance, if you have a 4 gigabyte FAT32 petition, just the FAT table will be about 2 megabyte. You must have at least 2 megabyte RAM to catch it, and otherwise hard disk access will be terribly slow. Now in the case of a FAT16 petition, well, the table is about 128 kilobytes, much smaller. But if you have, say, 5 of them, of course you have almost 1 megabyte. Now, look at the gbuffers protected. You see it is still increasing, and also another thing happens. The parameter SLRUN, I call it SLRun, but that's not correct, I'm afraid. With the big N, that's the maximal amount of buffers that can be protected. So that's the maximal amount of files you can have in a big file server. But if you just do a tree test, in this case, you see that if it would be a very big file server, because the tree test approaches all the metadata, and that was last accessed, then everything that went in first would be thrown out first out. First in, first out. That's the catch algorithm. Now, we go back to StarOffice and we have a look at this one. So you know, we have 3 segments. Protected segment, for instance, very important for a large file server. You would have at least 2/3 of the cache just having loaded with files of the people who are typing Word and other things. And you have a probationary part. In the case of my, if you just read in a file once, it's in the probation part. And if it's not used again, just like a newbie you have taken in your firm, and you notice, well, in fact we needed you, but we have not worked for you anymore, you would throw out first. And we have the free buffers, which could be used to load in new things, but also to do input-output. Now, if you have a large file to be read, and there are not enough free buffers, which you always can check yourself with using the SeeStats utility, then what must happen? The files must first go into the free buffers. So if there are not enough free buffers, now this file is bigger than that block, you must make space for it. Now the first things that go out of the cache are the probation part. It's not protected, it has been used once to read in a file, and it has not been accessed after that, so it's very logical to throw that away first. So these things go back. If they are just read in, it's just discarding buffers. If they have been written to, of course, you must lazy write them to disk. Then the next ones that are thrown out of the cache are the protected parts. And that's why you see this is 2/3 of the cache, and then it has to decrease, because otherwise you cannot load that large block. Well, that gives reorganization, just like you have reorganization when a new firm has to be, well, 2 firms have to fuse or something like that, and some people get in new and other people must get out. And that's also very complicated. Now I've written down something about the systems. The cache uses, just like other caches, the least recently used buffers mechanism to discard or write to disk free buffers. And the idea of keeping it segmented is simply because if you just use the catch algorithm of first in, first out, it means that, for instance, if you first loaded the directory OS2 and the directory del, and then you read in a big file, say you want to play an MPEG file, then the MPEG file is last gone into the cache, and if you have not the most often data protected, it would throw out most precious data. Do you understand that? Is that clear? Because it's quite fundamental. Right. Now something about other settings. SeeStats is so it's interesting if you want to know. Oh, how does the what is catch doing? You can also make logs of it. Yeah. Let me show that. You can make a utility that just do SeeStats, say, every second. Well, I have a better one. This is one. The utility I use is just a rec script, and it does SeeStats and puts it in a comma separated file. SeeStats logging, catch stat logging I call it. And it can be done very nicely here. You can see that you can, it gives a timestamp and also tells you what is the statistics of the buffers. You can make nice pictures of it using Lotus or OpenOffice. Now in this case is loading and saving a VPC guest. You can just see, oh, what does that mean to the cache? In this case, it was 385 MIP. All right. But I wonder if it was really 385 MIP because it could be compressed. Oh yeah, this is nice. This is just, I think I cannot start the rec script via the config.c, so I must use startup CMD for it. So it's the very first things when loading OS2 is not shown, but it's a nice demonstration of what happens. The red thing is just the cache size. In this case, it's about 17 buffers, and 70 buffers of 4 make a 64 megabyte cache. Then this sign here, that is just a static variable. 2/3 of the cache is the SL run variable. I think it's something like static LRU number. Then you see that very soon after well, this is every 5 seconds, so it should be something like 20 seconds. If here's about 10 seconds, it should be, no, it should be later. But very soon the cache is saturated. It's here. You can say it's at least 50 seconds after loading the startup CMD. The cache is saturated. It means that you have the situation of I've shown earlier. This is the situation which happens then with a small cache, and that means that every new file that is read in also has to give a reorganization of the cache. Now, if you increase the cache size, I will always do that. Yeah, I did a series of tests from small cache to larger cache. You can see that in this case, this is an indication that the cache, this is the rate at which the cache fills, this one. And you see it's normally, I think, a logarithmic function with all caches in fact. And you see here, nothing, it cannot grow, it's just flat. Here you see with 64, it still can grow till about 30 seconds, then it stops growing, and everything means everything that is read also means other data have to go out of the cache. If you make a larger cache, you see the logarithmic function starts rising, and here it even keeps on rising longer. So using a larger cache is certainly useful because if you have more free buffers, you can load files faster, much faster. But we also have seen that if you have a very big cache and little free buffers, and you suddenly load many things in the cache via heavy input-output, you have problems. Now, many problems, it's interesting, have been described in the past, and I would like to show you two. Cache overhead. No. But it has been, we had problems in the past with NetBench tests on journal file system, causes a hang due to insufficient free cache buffers. Large Xcopy on a journal file system drive leads to a hang. I think many of those problems were first happened on single core processors, and very often had to do with, here, this is the time of very high input output. Here you see it, here you see it again, here you see it again. That's just happening during, for instance, a disk input output test. And I really have seen it. Yesterday I showed to Jean that it's really hanging. But the funny thing is, if you have a SMP processor or just a dual core, you have no problems with it. It just works. And that's also a nice thing about JFS. It was designed for SMP systems. Right. Now, I just want to say something about memory timing. Timing of synchronizing. When Warp Server for A business came out, the sync timings, let me see, here we have it, were long compared to the current ones. Now we have lazy write, we have 5, 20 and 4 seconds for sync time, max age and buffer idle. What does it mean? The sync time is that every 5 seconds the cache should synchronize. I think that's stupid, because normally, in this case here, there's no reason to every 5 seconds synchronizing on a laptop. It's just stupid. I mean, it gives disk access, it can wake up things. I would say, just if you have a laptop, maybe make it 128, why not? There's no reason not to do it. The other thing is that max age, it was 256 seconds on Warp server. Yes, of course. If you have somebody on a server just typing words, just doing a control save every 10 minutes, why should you then just update the cats every 300 seconds or something like that? Well, could be longer. And that the buffer idle setting, well, for each high performance file system, it was just half a second. It just meant that every half a second, if a buffer was not approached, it would be discarded, logically, because high performance file system only had 2 MB of RAM. So if you want to have a high input output, no, it was a small but very dynamic organization, right? But a high journal file system cache is a very large cache. It's a large organization, and so you don't want to have a high turnover. In this case, the web server said just look at the buffers every 8 seconds. If a buffer is not used during 8 seconds, you can discard it or just do something with it, but not keep it. And if you approach it within 8 seconds, it could be a protective buffer because it has one cache in. Now, again, Ecom Station said, well, we wait 4 seconds. Well, why did they use that? Nobody documented it. Sometime at a certain moment in the news groups, you saw a message, somebody from IBM, nobody mentioned, said we need to do this and to safer to solve bugs. But the problem is nobody documented it. And there's still not reason, certainly not on SMP servers of just dual core systems, to use the larger cache settings. Linux does it. Really, on the Linux you also do not synchronize every 5 seconds. It's ridiculous. Just use the normal cache settings where the big and large caches are developed for. That's my idea. And the only thing, you should not do it if you suddenly one. Now, I think several things you should not do it. First, if you have a 1 GB cache and 700 MB is precious data from files that has been updated very often if you have a file server. Of course, you must be careful with that stuff. Then you would probably, well, in first instance do this, just the originally IBM settings, and at the moment you do something dangerous for the catch, just doing heavy input-output, for instance, big, large backup, or playing Doom, or just playing movies on the server, of course, you then could change the lazy write settings. And you can do that just if you want to. Sorry, wrong one. Well, if you want to change that, just do it with the setting of catch your default file system. You can do it just before doing your job. Well, that's, I think, the sense of tuning the catch for your job. What? Questions?
Programming session, you change the settings before and...
Yeah, no. It's very easy. Yeah, of course. It's very easy. You just do catch, well, oh wait. The tree test is finished, so you see, GBuff protected is not that much more. Yeah, catch JFS. You ask first for these things. Oh yeah, it's also interesting. The standard min-free buffers for OS2 are much too small. It's about half and 1% of cache memory. So in this case, it would be well, few megabytes. I here have a cache of 400 megabytes and gave, in this case, 100 megabytes to the buffers, more than 100 megabytes to the buffers. And why do I do that? Well, because I do sometimes some input-output testing during presentations, and you know, if you do heavy file input-output, yeah, just increase buffers. Now, yeah, if you say I want to change lazy write, it's just LW and then just typing. Well, I do now lazy write every 120 seconds. I will write to disk. Just try it. Now, every hour or something like that. I don't know if it fits, but just try it. Well, accepted. And it's still running. In this case, it would be a nice setting for a notebook, because you don't, if you have a large cache, probably everything you do is almost filled to memory. And also the free buffers you can change via min. Now you have to give the settings in buffers. Well, it's now 32,000. If I would like to have it just to test it, very strange and dangerous, I guess. 2 and max 5, which is a little bit like DOS. Well, let me see. Did he accept it? No, he didn't accept it. Oh yes, I have seen. Yeah, that's because he accepts it. Well, I never would advise this one, but let me see what I have. If I do a tree test, no. Well, it still works, but I don't expect it to be very fast. And if I really want to stress my system, I would do now a sysbench. That should also be the end of the demonstration, because I expect it to, to stop. No, it won't stop because I have a multi-core system. But if you have a single core system, you could now say goodbye to your show. Right, other questions? Nobody tweaked the buffers until now? One of the most stupid things I personally think it was that the free buffers standard are very small. I think this could be the standard settings. Right. But if you have a small cache, 64 MIP or something like that, you have maybe 1 MIP or 3 buffers, and that's a lousy thing compared to Linux and other operating systems with a virtual file system, which is as large as RAM is, and even placed in virtual memory. Oh yeah, this is also an interesting thing. When it comes to disk input-output, major delay is in the file system. Because if you, where was it? If you do disk input-output, just reading disk sectors, it reads about, in this case, this is a slow laptop, 30,000, almost 25,000 kilobytes a second. And you see, drive catch bus transfer rate is almost the same as the data transfer rate on cylinder 1 and on the last one. Now, cylinder 1 is the master boot record. Don't expect disk I/O to understand it. Just read the cylinders without interpreting them. If you just do lazy raw writing and reading, it's super fast. No need to be cached. In fact, it is faster uncatched. But the main reason always to catch things is illustrated in a file, in this one. I have a very nice, this one. How NTFS reads a file. Below is an example of what occurs when NT file system goes to read in one cluster file, Flintstone's Barney text. Well, it first reads the boot record to get the location of the master file table, which is something like the FAT table and seeking center of those two. Then it has to locate all the pieces of the master file table, because it can be fragmented. Then it goes on, has to find the root directory, has to find the Flintstone directory, and then has to find the location of the Barney directory. All times you need to have a disk header movement just to find the right, to go to the right sector. Well, in a worst case scenario, on an unmounted flume, 10 slow hard disk header movements are needed to find and read Barney text. 9 to find it, 1 to read it. That's the essence of caching. But if you have done that once, next time you don't need to have that 9 other things. And so thread checks can be approached in one hit. And all things about cache design have to do that with that. Hi. Other questions? Have you heard about double buffering? Single buffering? Why is it takes it so a long time before you open the Explorer in Windows? Anybody? What do I have? I'm looking for a picture about it. I have another one here. Let me see. Double caching is some operating systems use the virtual memory for caching. I have a picture of it. It's a drawing. Dynamically tuning. Should be here somewhere. Another version, I guess. If you have want to read the conferences file in Windows, well, we already have seen that I think about 8 disk movements are needed to find the file. It's in the root directory, so it's found earlier. But then it is copied to buffers, and when it is in the buffers, it is copied to the so-called page cache. They have a double caching. Oh shit, it was here. No. They have a page cache. Now I have a picture of it, so I would like to show you. Let's file in GIF. JFS buffers. Where is that? Let's cache and be coffee. Well, it makes if you OS2 has to free buffers when you read in new data. We have seen that. It forces to synchronize the cache. NT does the following thing. It can do several things. It can lazy write a buffer cache, but very often it reads the buffer cache content into a so-called page cache. It's just a part of virtual memory where the page where files can be let down. Now, if NT and also Windows XP have not enough virtual memory, they swap files to disk. And so if you read the convert.sys file, it might happen that the program first requests the buffers say no, we have not here, then the buffer cache approaches the page cache, and the page cache says, yes, we have it on the disk. So it's caching a file on the disk. Well, and nevertheless, this is faster than not doing it, but because also OS2 used a similar thing when it loaded the DLLs first in memory, when we had 4 or 8 megabytes of memory, and then put it on the pager, swap that. And it could be loaded from there faster than just from disk. All right, it's late, we have for lunch.